I'm recording this on Saturday, but it's for Friday's class. And I don't think I have never spent as much time preparing for a class wrap up as I have for this one. I think about 3 hours because the material has ramifications for this semester, next semester, your calculus classes. So it's an important one. I'll try and get through it in an hour. All right, so here we go. I'm going to share the screen. So it's for Friday 13th, Packet 2, Class 18. So we finished this up on Thursday. Now I know in class I assigned 10 and 11 as homework. We didn't have, and I'm going to start doing that, I guess. I hate to do it to you, but we've got to get caught up. We're too far behind. So some things I will assign as homework in class, and then I will go over it in the wrap-up video. All right. And on Thursday, we did a lot of this, looking at vectors through time. This is for, these are basically like 14 and 15. They're basically trios on their side. And from this, we found out that K equals 1/2 A. So we came back over here on this trio, and we had it as X equals KT squared. And now we can write it more specifically as X equals 1/2 AT squared. And it turns out this is true for any object that is falling or is accelerating at a constant rate. That is how the position changes with time. And if you follow the blue pattern, since it is a pattern, the diagonal pattern, we can then rewrite the velocity equation for jerk situation, for in the quartet. The velocity equation now, instead of being v is equal to kt squared, follow the same pattern, and velocity equals 1/2 jt squared. Okay, so that's all reviewed. Now, today's physics, we're going to concentrate on this trio, and this is a negative trio. It comes from the activity, which if you go back and look at the last wrap-up video, that's the ball. We went out in the hallway, and students put a cup down, and we rolled a ball up and down and timed it for a 3-degree ramp. Okay, so this was our data from Friday, it was Friday's work. There's our data. So this is a kind of a class average. Everybody has slightly different numbers, but asking around, this is the numbers I got. So the total time of movement of the ball going, so we used a little ruler to push the ball off of, so that once the ball left the ruler to when the ball came up the ramp, came back down, hit the ruler, that was about 6.6 seconds. So we are interested in half tau. That's called two-way time. We're interested in half tau, and that is the time it takes the ball to just get to the apex, or the ball to get from the apex back to the ruler using laws of symmetry. Well, since the ball left the ruler at about left the ramp at 25 centimeters, it took a little skill, but the students got the ball to go up to almost the edge, and that was around 225 centimeters. So as a class average, once again, it'll slightly differ. We said that the delta x, the one-way delta x, was 200 centimeters, okay, to the apex. And then the velocity at the apex is temporarily 0 because it's turning around, right? The ball is turning around, coming back down. Okay, and so we're supposed to figure out the acceleration of the ball, and that is the hard part. Okay. So we'll spend the whole time on this trio, and I've got, the reason why it took me 3 hours is I have a series of slides where I try and work my way through this concept. Okay, so we start off with what I told the kids was, since acceleration being diluted gravity, we only have one force acting on this. So we have one source of acceleration. So when you do that, you have a trio, okay? Now we're getting the forces here, start getting forces more after Thanksgiving, but forces cause masses to accelerate. So there's only one force acting on the ball, and that is gravity. Now you go, wait a minute, but isn't the ball being held up by the ramp? That is true, but that force is perpendicular to motion. That's what's called a contact force. The old way of saying it is a normal force, but we'll get into that free body diagram a little bit, maybe when we talk about this on Monday or Tuesday next week. All right, so we established that it was a trio. If that's the case, then we know that the acceleration down here, this would be flat, this would be linear, and this would be parabolic. And so maybe the first, so you're thinking in your mind, okay, flat, linear, parabolic, but then we go, wait a minute, it's actually, that's not true, because this would tell me, if that were true, it would tell me that the ball is continually speeding up, and it doesn't. In fact, the ball is going the fastest it goes right when it leaves the ruler at the 25 centimeter mark. It slows down until it reaches the apex. Then it speeds up, but in the negative direction after the apex. So this can't be right. So this is actually a negative trio. And so we know if we're a negative trio, it's the same idea, only now acceleration is still flat, and now it'll be in the fourth quadrant, just in general. Acceleration will be in the fourth quadrant. This will be, that puts it at a negative slope, right? So that will be a negative slope, and this will be parabolic, but it's got to be a negative parabola. So in that case, erase this. We know that this will be some type of negative parabola, so it has to either be like this as a negative parabola, or it could be coming up, and then slowing down. That looks, at least to the apex anyway, that looks better. So my general shapes of my graph then are going to look something like this over here. Okay, just in general. So now we go over here and we can look at this in detail. And here's the first panel I put together. The ball starts off rolling quickly. So this is the fastest the ball will be. And if I draw a tangent line, my green lines here are tangent lines. Remember, tangent line, the slope of tangent lines gives you the actual instantaneous velocity at that moment. And so you can see this curve, I'm a little shaky hands, but this curve is slowly losing angle. It's slowly losing its slope as the ball gets from where it started to the apex up here. That's the apex. Apex is always the highest point the ball gets, or if you're jumping over a creek, the highest point that your body achieves, your center of mass, that's the apex. Okay. All right, so the ball starts off moving fastest at the beginning, and then it starts to slow down as it reaches the apex. And then also I wrote up here, notice how the slope of these tangent lines, remember tangent lines kiss the curve at one point, and the slopes of these green tangent lines are getting less and less until finally you get up here at the top, and the slope of that tangent line, get the green going here, slope of that tangent line is flat because at the top there is no velocity, just for an instant. Okay. So I did all this pre-work so this discussion went faster. I didn't sit and watch you write a bunch of things down. So if we continue on here, this axis of symmetry, this is called the axis of symmetry. All right. The idea of symmetry is really big in physics, and really it's big in physics, it's big in chemistry, it's big in biological systems. This for like biophysics, things things tend to be like the water molecule, you know. You can draw these lines of symmetry through molecules. You can draw them through DNA. You could, but in physics, you can draw them through graphs, and it shows that the first part of the graph is symmetrical with the second part of the graph. All right, and that's because now this is assuming that there is no there's no friction. There has to be some friction or the ball won't roll, right? It would just slide. But we're calling that, I'm gonna call that, quote, rolling friction, which is enough to get it to roll, but we're going to say not enough to cause it to drain enough energy out of the system, all right? So we're in a bit of a fantasy world here, but the further you go in physics, the more real the situation gets, but then the harder the math gets. So we're getting there. We'll be at much more complicated math by the time April and May rolls around. But for now, all right. So since this acts as symmetry, I can then draw the second half, where the ball is from the apex back down to the ruler, and just use the same distance from the axis of symmetry as I did when it went up. So I have it all set up here. Let's see if I don't have too shaky of a hand, not too much coffee going on. So let's see here, something like, I can smooth it out. Remember, nature paints a broad brush, so I kind of fill that in. So this is my negative parabola, okay? I'm not crazy about it, but that does look pretty symmetrical. Not beautiful. All right. So this is a better job of that. And now looking at all those tangent lines, you can draw a tangent line at every microsecond, right? And it's kind of like an archway to a building. Those tangent lines will eventually form an arc. And so, yeah, so these slopes here, this is the idea of symmetry. You don't need to draw the tangent lines. All you got to do is draw the orange parabola. Okay. Well, I bring this up, and in class, I have a little model of the St. Louis Arch, and I thought that when I was over there about 20 years ago, I thought, oh, I'll buy this, and then I could show it to my kids, you know, so this is what I'm talking about. Well, the problem there is that this looks like an upside or a negative parabola, right? But I did that for a couple of years, and I'd show the students, and you know, that's cool and all. And finally, Lenny Gibson, who's was a legendary math teacher at Norman High, he said, no, that's not quite it. So the formula for the St. Louis Arch is this. It's a hyperbolic cosine. Now, that seems strange to me. I looked it up on Wikipedia, and he was correct. So it's not really a negative parabola, but it's sort of an interesting side note. And I'm offering students points. I've had one student so far. And on the Facebook group, if you'll research this, where this equation came from and why they're using this equation, and then write up a paragraph or two, put that on the Facebook group, and you'll get up to 10 points. So 10 Facebook points. Remember, points are points. So, all right, that's a side note. Let's keep back to business here. So here we are. We are now ready to plot the slope graph of these. And that is the slopes of those tangent lines. Remember, as you go to the graph below in a trio or in a quartet, doesn't matter, duet, the graph below is always the slope graph of the graph above. So that would be a V versus T in this case. And so you break it up into two quadrants, first quadrant, fourth quadrant. The first quadrant of a V versus T graph would be represents the object moving forward. So anytime the object moves forward, as if you've done the finger dance, maybe you got that, you figured that out. I mean, I think I'm realizing how important that finger dance was, and now I'm starting to regret just assigning it as extra credit. You know, Rylan seemed to understand this stuff, but I watched this guy ponder that finger dance for an entire lunch period, and then it all kind of started coming to him, and then that made this easier. So there's just no substitute in physics. There's no shortcuts. You have to ponder the material. If you're not willing to do that, you're not going to get very far in physics. You can't memorize your way through the class. You know, you can't BS it. You can BS it some, and maybe pull a C, but you cannot. It's just you have to actually put in the time. Okay, there's no meme I can show you that's going to make it all work. You've got to actually, you know, and it's frustrating. I mean, it's hard to think through things. That's why I put these puzzles to you and see what you come up with. Anyway, so the green first quadrant, it represents anything forward. So anytime there's a velocity there, you're moving forward. The blue fourth quadrant represents the object going backwards. Okay. So now we plot this. Well, how do I know it's linear? Well, I know it's linear from all this pre-work we did. If this is parabolic, if we have something, we know that this, we know this from that previous from 2.8. If this is x equals kt squared, and now we know from our previous work that this is something, x equals 1/2 at squared, okay? And then this one, actually that is not the equation for that, because it did not start at 0. So this has an additional part to it. So I'm going to back off that. That's going to give you a misconception. Let's just say that in general, very general, it's x equals kt squared in general. Only one more than alpha. So if that's the case, then we know that v equals some other kt, right? Actually, at least we can say this: v is equal to at, okay, plus some v naught. And this time we do have v naught, right? I mean, this right here is our v naught. So that's going to be the equation. But the point I'm making is, if this is parabolic, then this is linear, this graph. So I don't know. A student asked, well, how do you know to start right there? I don't know what that number is. I don't know what v naught is yet. I could get a ballpark figure and find the slope of that tangent line, but it would be a guess. I mean, now we're having the problems that Newton had. So, oh, by the way, this down here would be, before I forget, this would be A equals some kind of K, right? Well, we said A is equal to A naught. So it has some acceleration that it keeps the whole time. We just don't know what they are. So we know this is going to be flat. We know this will be flat down here. We don't know what, but where, or what it's going to be flat, but we know it's flat. And in the fourth quadrant. All right. So what I did was, I didn't put any numbers. Notice there's no numbers along here yet, but I do know the shape. I knew that it'll be linear. I do know it'll start here. It'll end up down here, because it starts off, the marble starts off rolling positively away from the origin being the 25 centimeter mark. We're going to call that 0. And then it's going to end up coming back there. So I know this is symmetrical. Okay, keep going. Oh, back here, let's blow this up. So this little point right there is the apex. That's where it crosses. The apex is where it crosses from the first quadrant into the fourth quadrant. From going forwards to going backwards, that's the apex. That's a turnaround point. But that matches up with the peak on the parabola, all right, the highest point. So those are both the apex. Okay, so now it gets a little more complicated. I fill these in, and these, okay, remember, as you go from a graph above to a graph below, that's slope. But if I go from a graph below to a graph above, that's area. So I am trying to, one of my goals here is to find out what the initial, I really have two main goals. One is to find out what the initial velocity of the ball is, of the marble coming off the ruler. And the other is, okay, I'm gonna say three goals. The other is find the acceleration. And then the third goal is see how much we diluted gravity, how much this inclined plane diluted gravity, in the words of Galileo. How much are we, like, gravity is, gravity would be the ball, just me throwing the ball in the air, then it reaches its apex and me catching it. That would be, but the problem with that is, we've done this before. We did camera, and we tried to, you just don't get enough data. So instead we decided to go with the inclined plane, similar thinking to Galileo. Let's slow down. So the gravity is still the thing that is causing it to go up and down the ramp, but let's increase our time so we can actually study it and draw a graph like this. Okay, so three things I want to know: what's initial velocity, what is the acceleration, and what percent of gravity? How much did I dilute gravity? Okay, so this this green right triangle in the first quadrant represents, not UPS, ups. It represents ups, all the ups. The ball's going up, 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 up. The blue in the fourth quadrant right triangle represents the ball going down, 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 down. Okay, this is true. We're going to study free fall here later on. We're going to study projectile motion, which is basically the physics of sports. We're going to study that. But this all holds true. A lot of things. This is why I spent 3 hours preparing this, because this will be the foundation of a lot of what's happening all the way through January, even some spilling into February some. And then we also come back and do these kind of graphs when it comes to forces and, inertia and all that stuff. We still come back and do graphs, and we still do derivatives. Okay. So this, we'll blow this up so you can read it. This green then, calculus would call this the positive area. This represents the gain in position of the ball as it moves up the incline. So the area under, this is the tenet of calculus. Calculus, the word means a building up, right? You get calculus in your teeth, and the hygienist has to scrape it off. So it's a building up of layers. Well, that's what this is. I am growing, as I move left to right through time, I am gaining position. I'm going to go into detail on this in a second. Now, it's diminishing returns. You've heard of that phrase. It's diminishing returns because in the first second, it's like front loaded. I get all this, there's a lot of connections to finance with this, because there's something called business calculus. So if you go into business, you'll have to take business calc 1 and 2, maybe even 3. But you are looking at trends. Anyway, this is considered front loaded. So in the first second, so all my movement is front loaded with the first second. Most of the area here of this triangle occurs in the first second. The second from 1 to 2 seconds, that area is not as great, because I'm not accumulating as much position because the ball's slowing down. And then this triangle in the end, this 2 to 3.3 seconds, that's the least amount of bang for my buck, I guess you'd say. So that area then represents the accumulation of position. And then the blue area, calculus calls this a negative area. Now we've done this, we did this in finger dance, we did this quite a bit in the earlier parts of Packet 2 with Slappy the Clown and all, where these are, like, we call these stalactites. We call the green stalagmites, but we call the blue, remember we show the area from the axis down, and these are like a stalactite in a cave. So this is now growing, and now it's backloaded because you're getting more and more speed the further away from the apex and back to the origin it goes. So the marble now is picking up speed again, right? But it's picking it up in a negative direction from the reference point. As it's coming back to the reference point, that's a negative direction. So we show it as a negative, coming back down. And the other thing I said on here, I said the V versus T graph is called this particular V versus T graph is called the perfect bow tie, because this is congruent to this. And that makes this easier. Now we're going to have, later on, we're going to have skewed bow ties. It turns out with projectile motion, there are 7 possible situations, and we'll go through those 7. This is like throwing say a watermelon off a building. That's one. Throwing your keys up to somebody in the 2nd floor, they reach your hand out and grab them. That's 2. There's 7 different ways that projectile motion can work. So I'm getting way ahead of myself now. But anyway, this is projectile motion is I throw something up and it's caught at the same height that it was thrown up at. Okay, what do we got next? I made some stuff so long ago, I forgot what. Okay, so the still comes down to this. The question, one of the 3 questions, remember, is what is one of the first questions we have to answer is, what is the initial velocity? I just kind of left it as generic, but we have to have a value there. So, okay, we already talked about all that. All right, let's keep going then. All right, so here it says, all right, so in other words, what I'm really asking is how fast did the ball come off the ruler? You all used a ruler to kind of scoot the ball to the 25 centimeter mark to give it some initial speed. That's what we're asking, okay? Now, so just remember that the graph above, this graph here is showing the accumulation of position or area here, but it ends up being position up here. And the reason why area is position is because this axis is centimeters per second, and this axis is seconds. So centimeters per second times seconds gives me centimeters. So this is a tricky situation. You can throw this one by your math teacher. You can ask your math teacher, teacher, when is area the same as length? And this is the case. I used to say that all the time. And so Gibson Lenny was sort of my nemesis. Well, I mean, he was my hero, but so I said, hey kids, ask Lenny, ask Gibby, when does area equal length? And he snapped right back. He said, oh, well, if you're plotting, like velocity versus time. Oh, man. I couldn't get that guy. Okay. And so any area here in this graph will show up as position up here. And I'll just say, I'll do a running total as I'm accumulating it. And that's, you can see that this is what I talked about, diminishing returns being front loaded. You get a lot of area, a lot of position gained early. And then as time, it kind of peters out until it reaches the apex. And then we start to pick it up again, but in the negative direction. All right, still trying to figure out what the initial velocity is. So to answer this, we start up here. To answer this question, we need to use the formula for the area of a triangle, which from geometry is area is 1/2 base times height. Okay, you got to have that for the ACT and the SAT. The ACT doesn't give you any formulas. The SAT does, but then they expect you to use them in strange situations. So pick your poison. Anyway, the ACT is more of a blunt instrument, I guess. And the SAT, I think it came from a Stanford Binet. I think it came from a psychological exam. SAT has interesting history, but they're more like trying to figure out, that's the national merit, right? $40,000 or next to $50,000 now. You get if you do really well on that. But they're trying to see if you can figure out, if you can think your way out of a box, at least puzzles, give you all these puzzles. So it's a pretty good intelligence test. ACT is more of a blunt instrument, kind of, do you remember this formula? Do you remember this formula? So I don't know, some people like one or the other. I know the base here, so I already know the base on my green right triangle. I already know the base is 3.3 seconds, all right, because that's, that's symmetry, and I knew it took, I already knew, I already had it figured out. So I know the area of the green ups triangle is 200 centimeters. Now I know that because this graph is measuring area, and I ended up at, blow this up a little bit so you can see it, I ended up at 200 centimeters. 200 centimeters. So I'm using the graph on top to help me with the graph on bottom. All right, so then we keep going. It says, well, now all I have to do is solve for the height of the triangle, and that will be the V naught for the ball. So my formula then, area is 1/2 base times height. If I'm going to solve this for h and multiply both sides by 2, they get sort of the 1/2. Now divide both sides by b, they get the h by itself. I always put my isolated variable on the left side. That's sort of standard practice. So h equals 2a over b, so we have 2 times 200 over 3.3. Or if I did my math right, hopefully 121 centimeters per second. So we are saying that when that ball came off that, and that's like magic, like we figured that out just from the graph. That's kind of cool. So when that ball came off, this is thinking like Newton, right? It gave him a chance to understand instantaneous. Remember, Newton was obsessed with being instantaneous, not being average. That's why he invented calculus. Okay, so it comes off when you first let it go off the ruler, it comes off at 121 centimeters per second. Pretty fast. Okay, that's 1.2 meters a second. So that's about the speed at which you walk. So it's not like a shooting, not like a speeding bullet or anything, but still pretty fast. Okay, keep going then. So we got that much. We know it's 120. Let's play with that for a second. And I want to go back and look at this idea of this diminishing returns. So in the first second, the orange part here is this is how far this area here is how much of the incline that the ball accumulated, how far up it got in the first second. And then the blue is how far the blue trapezoid, the area there represents how far the ball got in the second. And then the the kind of a reddish pink, whatever, triangle, that's how far the ball got in the next, not really the third second. I got to fix that. It's not really the third second. It's the next 1.3 seconds, not the third second. So this was in the next 1.3 seconds. So we went all the way to 3.3. So sorry, correct this 3 point in the well, okay, sorry, 1.3 seconds, total of 3.3. Corrections. So in the last 1.3 seconds. Sorry. This is supposed to go fast. In the last 1.3 seconds, the ball does not cover much distance, right? Diminishing returns. Okay. So that's the only thing to do on that one. Let's keep going. So now I've taken that and kind of broke it down. Do a little math here. So we start off with the orange. So the area of this trapezoid represents how much position the marble accumulated in the first second of rolling. Oh man, I'm messing up here all of a sudden. Okay, so the area of the blue represents position the marble gained in the second, and the area of the, okay. So I thought I had worked that out, but somehow that did not get on here. Let me pause this because I had that worked out somewhere. I'll come right back. Okay, so I'm back. I deleted, I guess, a while ago, the wrong slide, so I can redid this one. So it's more specific, like here in the first trapezoid, that represents how far it went. Well, I can actually look up here at the graph, and the first second accumulation, it looks like it goes to 125. That's this, with about 125 centimeters is how far the marble got in the first. That is the area. If you run the numbers on that trapezoid, you will get 125 or close to it for your answer. So that's what I wrote down here. According to the accumulation graph, that is about 125 centimeters. So then for the second, that's the blue, and the position of the marble gained in the second of rolling. According to the accumulation graph, that, now I go for the blue part, that is 175 centimeters, which is at this point right here, minus where it started at 125 centimeters. So the ball gained 50 centimeters in the second. So it's losing ground, diminishing returns that we talked about. And then the last little bit before it gets to the apex, that last 1.3 seconds, now that is this pink part. You see, you're not getting much height from that. And that one, it looks like we're only going to get about 25, according to the graph, only going to get about 25 centimeters. So 200 centimeters minus 175. So you went from getting right off the bat, getting 125 centimeters, and then the next second it was only 50 centimeters, then the next second was only 25 centimeters. Okay, and then the same thing happens on the other side. So the first part of that you would lose 25 centimeters on the second part, then you would lose 50 more centimeters. Okay. So now a total of 75 centimeters, and then you would lose the 125 centimeters. So you end up being losing everything you gained. All right. And you can see this does have your financial, this is called the derivative. This is the derivative of this function. And so derivatives are kind of telling you the derivatives is a huge thing in finance. You make a lot of money if you understand derivatives at Wall Street, kind of looking at trends and looking at where the thing's going to go, futures, that kind of stuff. But you can follow the trend lines and see which way it's heading. So I think these are forecasters. One of my old students, Martin, is doing very well in Chicago doing this. All right. So I think the last thing we have to do on this is to figure out the acceleration, that's pretty simple. That's just the slope of this line. All right. Now that we have the numbers, we can figure out the slope of this line. So so I'm saying that's easy. Just the slope of this V versus T line. So I went back and redid it, just looking at this as our typical upside down right triangle is because it's upside down because it's negative. And so we're just finding rise over run. Well, it's going to drop. Remember, it started off, this value was 121, I think. Yeah, this V naught was 121 centimeters per second. So yeah, this is 120 centimeters per second. So then this must be negative 121 centimeters per second, right? Because it's symmetrical. So you add those up, 242 is how much it dropped. It's how much the velocity changed. So the delta V is negative 242 centimeters per second. The delta T is 6.6 seconds. And so next one, we then can do the math on that, and we see that the acceleration of the ball, and it's constant. I know the ball changed motion. I know the ball went up and when turned around, came back down. But it's the acceleration that's running the show. And that was constant at negative 36.7 centimeters per second per second. So every second that ball was in motion, it was losing 36.7 centimeters per second. Okay. So, and then as a reference to this, so we've answered the question now. Three questions we had. One was what's the initial velocity of the ball? We got that. The next was what's the acceleration of the ball? And then the third question is how much do we dilute gravity? So as a reference, the acceleration due to the Earth's gravity, if I were to drop a ball just without any kind of ramp, would be 981, and we'll do the math later on to show this. We'll go to the stadium and drop things, prove it to ourselves. 981 centimeters per second. So our 3-degree incline then, playing diluted gravity, the difference there between 981 and 37, it diluted gravity by 96 and divided that by 981. We diluted gravity by 96%. So that's pretty good. That's why you can slow it down so much. Okay, I think that's it. Yeah, so to-do list then is to work on take-home test 2A. So stop sharing, and hopefully that helped. You can go back and watch. That's the good thing about these. I know I have some fun on help videos I did this summer on this stuff, so I'll try and track those down and also include those as links. I need to do a better job of getting behind. And we have all these wrap-up videos, and that's great, but there are some specific videos about this which goes through it as well. It's not so long, 5 minutes versus I don't know how long this was. All right, well, have a good rest of your weekend, and I'll see you guys Monday. Bye.